commented this morning that Go was meant for server-side, not for embedded work. Oops. Fortunately, hardware is still cheaper than software developer time, and perhaps more relevantly, it's easier to hire hardware than it is to hire software developers. So one of the things that I've been working on at PayPal is PayPal Beacon. Under the shiny industrial designed exterior is pretty much just an LED, a Wi-Fi BLE chip, a fairly low-powered ARM chip, and a Linux OS. And the main service that runs on it is written in Go. So I'm going to tell you some of the lessons I learned from writing embedded Go. But before we do that, I actually want to talk a little bit about Bluetooth. Bluetooth Low Energy is the new hotness, along with Go. Unfortunately, that hasn't translated into a lot of good documentation on the web about it, which means if you're interested in it, it's incredibly hard to get started. So I'm going to give you a quick overview, and then we're going to do something fun with it as a demo. So BLE is the 4th generation of the Bluetooth protocol. Like all the previous Bluetooth protocols, it runs on the same spectrum, namely Wi-Fi. It uses the same Bluetooth radio. However, everything else about the protocol has been scrapped and redesigned from the beginning to focus single-mindedly on being low energy usage. And the idea is that you should be able to create a BLE device, say a thermometer or a heart rate monitor, that can run for years on a little button battery. And everything about the protocol is dominated by the desire for low energy usage. So first of all, it's very simple. This is a requirement. If you do anything complicated, that uses CPU and that uses battery. So it's got to be simple. As a consequence of being simple, it's actually really low cost. It typically costs a manufacturer a couple of pennies to add BLE support to a Bluetooth chip. And as a result, pretty much everyone has done it, so it's ubiquitous. That's part of the reason everyone's really excited about it. It's very low bandwidth. We'll talk about that again in a bit. But also, interestingly and importantly, there's an asymmetry built into the protocol. So BLE uses funny words for everything. We have to get used to it, so I'm going to bring up to speed quickly in this talk. In the BLE world, there are peripherals and there are centrals. And a peripheral you can think of as a server. It's the thing that is going to be low energy usage. A typical peripheral is a thermometer. Your central is going to be something that's going to be connecting to your peripherals and inquiring for information from them. Typically, that's going to be your phone. And the asymmetry is there's an assumption that your peripherals are extremely starved for resources. They have little or no CPU. They can't consume much battery. Your centrals, however, are going to be fairly rich. Your phone has a pretty hefty CPU. It's got a battery. And anytime you can split up the work and make the central, your client, do more work, BLE makes you do that. OK. Because it's low energy, incredibly low energy, you can have it be always on in any device. And that turns out to be very useful. And I'm going to stop with the overview here. There's a lot more to say. If you're really curious about it, there's a very well-written book by Robin Hayden. Pick it up. So as a developer, if you're going to actually use BLE, you're going to write something on it. The level at which you interact with it is called GAT, the generic attribute profile. Forget about that. The idea here is, here's what's going on. Peripherals advertise services. So your thermometer says, hey, I'm a thermometer. It actually sends out advertising packets saying, I'm a thermometer. And these services that it advertises are nothing more than a sort of semantically grouped set of characteristics. What's a characteristic? I did promise. That's worse. Here we go. Cell phone? Sweet. Thanks, Russ. So I promised lots of new terminology. A characteristic is just a value, plain and simple. You can read the value. You can write the value. You can request notifications when the value changes. And the other interesting thing about characteristics is they're small. Think typically like 20 bytes. So characteristics are values. They're grouped up into services, and peripherals provide services. I did say it was simple. You're now an expert. The problem is, of course, like I said, it hasn't translated into a lot of good documentation on the web. It also hasn't translated it into easy accessibility for developers. So if you want to actually go build something, you end up mucking around in low-level firmware, which is what I've spent too much of my life doing. Fortunately, in the last 2 weeks, I scrambled to pull together a nice package for you guys as a GopherCon special. So if you want to write a BLE peripheral, you can now go do it in Go. And I'm going to add central support, but didn't have time yet. And for that reason, the API is not yet stable, but it's getting pretty good. For now, for your central, you can use your phone. So this package for the moment. It's going to expand. For the moment, it works with BlueZ, which is the kernel module that comes with Linux for working with Bluetooth Low Energy devices. So it works on Linux right now, and pretty much any flavor. You can run it on a Raspberry Pi. You can run it on a VM, which we'll see here. So let's take a look at actually using this package. We're going to have a server. We're going to give it a name, something memorable, and then we're going to add a service to it. Everything in the BLE world, everything in the GATT world has a UUID, typically 128 bits, and that's how they get identified. So you know exactly what the service is and what it supports based on the UUID. So great, we've added a service. We need to add some characteristics to that service. Let's go ahead and add two. We're going to add a write-only characteristic and a notify-only characteristic. These could have been the same one, but it's a little simpler to write it up one at a time. So our write characteristic needs a UUID, like all characteristics. And when a write comes in, let's do the simplest possible thing and just go ahead and log it. So this means the central has connected to us. They've discovered our characteristic, and they said, hey, please write this value to this characteristic. We're going to log it. The notify characteristic is a little more interesting. The central is going to connect. It's going to request notifications. It doesn't happen by default, again, to try to save battery for everyone involved. It's going to request notifications and say, hey, tell me when this value changes. So for this sample code, when this happens, we're going to spin off a go routine, and every second, we're going to tell the central that a precious second of its life has ticked away. And we're only going to keep sending these as long as the notification is still in place. So while the central hasn't said, hey, I'm done, I don't want any more notifications. OK, so that's it. We're all done. We ask our peripheral to advertise this service and accept connection. So let's do a demo. So we're advertising the service. I'm going to start up light blue, which is generic central. There are actually two BLE chips involved here. One of them is this little cheap USB dongle plugged in that's talking to Linux. And then the other one is built into my Mac, which is where the central is running. So on the central, we're going to go ahead and connect to, wow, there are a lot of devices here. So in the theater world, they say that you shouldn't go on stage with animals and children. And I think the tech world, you don't do demos involving RF. Nope, not that one. Somebody out there. So you'll notice actually it takes a long time to come up. Again, this is because everyone's trying to save energy. So you can see down here we've connected. Here's the service we created. There's a third characteristic here, which is actually a read characteristic, which tells us what time zone we're in. I thought everyone would appreciate that, although apparently my computer still thinks we're in California. So let's write something into the write characteristic. And it's been logged down there. Let's go and subscribe to notifications, and we can all sit here for the rest of 21 minutes and watch our life tick away. Or we can stop. OK, enough for the demo. Back to the slides. So that's great. Now we can write a BLE peripheral. We can talk to it with our phone, and you guys can all go home and play with your Raspberry Pis. In fact, if anyone really wants to play with it here, I brought a couple of these along. So if you have a Linux VM, you can have some fun this weekend. I'm happy to lend out these devices. But let's abuse BLE. BLE is for simple things, right? It's for little low-power devices with tiny little characteristics. We're going to use it to build a network stack, a full duplex network stack. And of course, the obvious way to do that is to do what the standard library would do. We need a net.listener and a net.connection. Unfortunately, we just introduced all the pieces. The BLE link layer provides us with connections. You saw that when I tapped on GopherCon, we saw a log in the Linux world that says, hey, somebody connected. And when I hit disconnect, it said, hey, someone disconnected. So the connection management piece is taken care of. Our write characteristics let us read data from our central, right? The central is writing to us, so we are reading from them. And our notify characteristic lets us push data back to the central, effectively write back to our central. So we have read, write. I promise you we can close the connections. Now all we're missing is addresses and deadlines. Addresses, we can just cheat and use hardware addresses. It's actually not a terrible idea because for security reasons, BLE rotates MAC addresses every 15 minutes. So they're a reasonable address to do. And for deadlines, we can just return errors and say, sorry, we don't support deadlines. We can fix that up later. As for listeners, we're pretty much already set. We have advertise and serve, which fires up, which takes care of the accepting case. Closing is just a bit of bookkeeping, and addresses, again, we can use MAC addresses. So great. If we can implement net.con and net.listener, we can do anything you want involving networks, Like, we could serve HTTP over BLE. It's really easy, in fact. You just take this stuff, and you get this nice net.listener, and you feed it into the HTTP's server. You're off to the races. Well, sort of. So I had this exciting idea. I was like, hey, look, Present, which is running these slides, it's just an HTTP server. Wouldn't it make an awesome demo if I brought in a Raspberry Pi and I ran Present, only I did it over BLE? OK, well, I'm going to have to write an OS X app because Chrome doesn't know how to do BLE connection. So I'll write an OS X app that uses a web view, and it will just do everything it needs to do. And I got it all working. And I discovered that by the time that you load all of the fonts and all the JavaScript and everything, it takes about 15 minutes. And that was in my living room. And while the organizers here have been very gracious about not putting any brown M&Ms in my room, I thought it was too much to ask them to build me a Faraday cage up here for loading my presentation. And why would I need a Faraday cage? Well, we're kind of doing HTTP over UDP. Those of you who might have noticed, like, hey, is there any guarantee of delivery there? And the answer is no. In fact, it's worse than UDP because we don't even have any muxing. So, however, like I said, there's a shortage of good documentation about BLE on the web. So this sample code that I wrote, which you can run in your living rooms, is going to be put up with these slides in the obvious place. So you can try it out yourself, and you now have a worked example of what an OS X central looks like and a Go peripheral looks like. OK, so that said, in Beacon, we actually do serve HTTP over BLE. We just have some extra layers. Right, your traditional network stack, you have a TCP/IP stack, which exposes a net listener. You write some HTTP handlers, and you hook it up, and you're off to the races. With Beacon, we start with this low-level GAT server using write and notify characteristics, which get exposed via a net listener. And then we have a custom transport layer, which provides the things that you would expect roughly from TCP, multiplexing and reliability. We didn't use TCP because the TCP packet overhead is 20 bytes, which is our MTU. So that wasn't going to work. We did something much simpler than TCP that worked for our purposes. And at the end of it, the awesome thing is it gets exposed just as a net.listener. Just the same way you can have a net.listener for UDP, TCP. The next layer up is a net listener. At the application layer, we have two application layers. The first one is protobuf messages. Again, if you have a 20-byte MTU, you can imagine you want to be really conservative about what you stick in there. You don't want to send a bunch of packets just to do anything simple. So for high throughput, high efficiency cases, the common case, we use protobuf. But there are cases where you care more about flexibility than you do about throughput. And in those cases, it's actually really nice to have an HTTP server. So there's a flag in our protobuf message. So you can say, hey, I'm sending you a raw HTTP message. We then bundle that up and expose it via net.listener to an HTTP server. And the awesome, awesome thing about this is we can write all of our HTTP handlers that do all the complicated, ugly, complicated work. We can test them using TCP/IP. We can test them using the HTTP test module from the standard library. And then at the end, we can just hook it back up to our BLE stack and have confidence that everything is just going to work. What's missing here also is security. So the underlying link layer is not secure. And that would be a whole separate talk, how we handle security. The short answer is it's complicated. Enough about BLE. Let's talk about embedded Go. So the first question you might ask is, why do I care? Because most of you follow a Rob's advice and you're writing server-side Go. But in the world of design, actually, there's this notion called universal design. It says, when you're designing a product, instead of designing for what you think of as your normal user, your average user, instead design for users that have the most challenges. Maybe they're low-sighted. Maybe they have difficulty putting in input. Maybe they're going to have an incredibly weak background in the domain that you're trying to address them in. If you design for everybody, for the challenging cases, you're going to end up with a better product for everybody. Really thinking through those challenges makes it better for everyone. So I'm going to claim, and we'll see if this holds up, that some of the things I learned about writing embedded Go, which has its own unique challenges, are actually very useful in the rest of the world. So what did I learn? Well, let's hit three things. Obviously, not everything in Beacon is written in Go. There's a Linux OS that's in C. There's a bunch of other helpers that are in C. You don't want to do anything real time. So somewhere you're going to have to draw the division of labor where this gets done in Go and this gets done somehow else. The guiding principle that we landed on after a bunch of experimentation is you do as much as possible in Go without sacrificing portability at all. You want 100% portability. And that means, in particular, no raw syscalls, no ioctls, and no cgo. What does this get you? This gets you all sorts of wonderful things. It gets you cross-compilation. So when we go to write our CI toolchain, it's really easy. You can compile it anywhere and pass it on down. It gets you testability, because everything that you do that relies on some lower level piece has interfaces. You can mock it. It gives you modularity. It gives you privilege separation. Now all of the C pieces you rely on can have the key privileges, and Go can remain very sort of low level in user space or high level in user space. It's decoupled from hardware churn. If you're working on hardware, you'll discover that the hardware guys are constantly fiddling with this, and now you have a kernel module, and we switch to some different LED, and it has a different bits fiddled here. By having an explicit interface boundary between Go and all the low-level stuff, now it's really easy. You say, hey, fine, expose the same thing, we're off to the races. Nothing needs to change. And in fact, we run the same version of our Go service across every generation of hardware, and we've been through several already, with no changes, which is a really nice thing. And it makes the hardware team feel free to make changes without worrying about the impact it's going to have on software. And it gives you some amount of sanity. The first moment I had when I realized I was just not going to use ioctls was trying to set up the right struct in memory. And there was a struct that contained a union that contained a struct that contained a union. And I said, forget about it. There's got to be another way. So what do? The picture I have in my head is of a gopher sort of hanging back, sitting in a chair, sort of waving its arms around, telling all these other gophers with an F to go do things for it. These gophers with an F are the kernel modules. They're some C shims. They're maybe some platform-provided UART connection, but it's exposed just as a serial connection. So this has worked very, very well for us. OK, GC. The reason I bring it up is actually to say it's not a big deal. And I mention it here because 90% of people who hear, oh, you're doing embedded Go, what do you do about garbage collection? That's all I hear from people. The answer is, almost nothing is what I do about garbage collection. First of all, the amount of time it takes to do GC is pretty small, milliseconds. And our user experience is dominated by the BLE link latency. And most of the stuff happens in the background while the phone is still in the user's pocket. And so they're not aware of a couple milliseconds. They don't have the opportunity to be aware of a couple milliseconds. So in the picture of the broader product, GC pauses just don't matter, as long as they're reasonable. How do you keep them reasonable? You write efficient code. And as we saw, Derek talked about earlier, Go gives you all the tools you need to write efficient code in the cases where you need to write efficient code. So you can just take advantage of it. Where do you need to write efficient code? OK, it's on the slide. One important thing to note, though, if you're worried about GC pauses, think about the number of Alex as much as you think about the size of the Alex. That's going to be the thing that drives the length of your GC pause. If you're worried about total memory usage, yes, worry about your size. But start with the number of Alex. Overall, though, I would say I have spent less than 8 hours over the lifetime of a many, many, many month project worrying about GC. The last interesting bit, many of you guys are going to be familiar with crash-only programs. The idea behind a crash-only program is it's very hard to, the idea behind a crash-only program is don't try to have a graceful shutdown path. Don't try to have a way to say, oh, I hit a sig hup. OK, I'm going to wind this down and tidy this up and close this network connection and write out this data to disk. Instead, assume that the only way that your program ever terminates is a kill-9, or you lose power, and your program is going to stop execution between any two instructions, and you don't know what they are. Writing a crash-only program says we need to be prepared for that, and you do all of your work on bring up. So, ooh. Yes, that was a really spooky point. You do all of your work. You do all of your work on bring up. You do any repairing you need to do. You need to make sure that anything you depend on is in a good state. Maybe that means turning off the BLE chip and waiting and turning it back on again. But it's your responsibility on bring up to make sure that everything is as it should be. So this is required for an embedded system. There's no battery in there. And at any given point in time, some merge is going to walk along and bump into it, and it's going to lose power. It's just a fact. So we have to write it this way. But it's also awesome. It's awesome for a couple reasons. One, it actually leads to simpler code. So we've all written for select loops, or many of us have written for select loops, where you're thinking, OK, when this gets closed down, how do I tidy this up? How do I get all these other pieces to clean up? What are all the blocks that are going to fall? For a lot of these cases now, you don't actually have an exit path. It's going to run forever. Don't worry about cleaning up. Also, with Beacon, pretty much all of Beacon is managing concurrency. I've got all these BLE connections, and over here I've got all these Wi-Fi connections, and over here I'm like fiddling with bits of the hardware and the LED. There's all these different pieces of state that you have to manage, and at any given point in time, some bit of the hardware is going to fuss out on you. All of a sudden, the BLE chip is not sort of responding the way it should. The LED is frozen. What do you do when you encounter that situation? One option is to write a bunch of recovery code. You say, OK, if the BLE chip isn't working, we're going to try to go in some loop. We're going to bring it down, bring it back up again. We're going to try to restore whatever state it was in. Maybe it was advertising. Maybe it wasn't. Maybe there was a dropped connection. We're going to figure out what those connections were. You could write all that recovery code, but it's a lot of code. It doesn't get exercised very much, and it's going to be fragile. Instead, something goes wrong, take yourself down. You get brought back up, and as you come back up, you put everything back into a good state. That code gets exercised every time you start, and it makes all of your recovery code very, very, very simple. And it makes for a much more robust system. It's very hard to get into an awkward state somewhere that you can't get back out of, because every time you detect an awkward state, forget about it, take yourself down, bring yourself back up. The other exciting thing is it's actually not that hard. You have to think a little bit about writing the file system and trying to make sure that your writes are atomic, doing an inode swap. And you need to make sure that you understand everything on which you depend and how to get it back into a good state. But that's something that you should understand anyway. So writing crash-only software is actually not very hard. And even if it wasn't required, I'd encourage you to really consider it, because it does make for, in many ways, a system that's easier to reason about, easier to maintain, and easier to understand. Got a few links here. The first one is a link to the GAT package, so you can play with it. The second one is where the demo code that takes 15 minutes is going to live. And the last link is to a little library that lets you hook up a generic I/O reader and writer, turn it into a net.con or net.listener. That's what we do for hooking up our raw HTTP buffer into a net listener to feed back to HTTP. It's just some boilerplate that takes care of it for you. And that's it, and I left enough time for questions. Let her rip. Right here.
So I really appreciate what you had to say about crash-only software. The project I'm working on right now, I'm trying to follow the same principle. So my question for you is something that I'm struggling a little with. How do you test that? Automated, repeatable testing.
Of the crash-only aspects?
Yeah, forcing it to crash in important places so you can test your recovery at startup.
Yep, that's a very good question. I don't know the answer. So I can tell you what we've done, which is not the full answer. What we have done is, through trial and experience, we have discovered what the painful places are. And it's pretty easy to set up a test rig that says, hey, you got a flag, please crash here. You check the flag. You take yourself down. s.exit is enough to take yourself down. So you can test manually specific parts. But the focus has more been around making sure that testing that your bring-up code is good. So worry less about where you go down and worry more about making sure that your recovery code is not fiddly, it's big hammers. Like when we bring up the BLE chip, I cut power to it. It's off. And then it comes on again. And it goes through the entire startup sequence. So I'm pretty sure that I'm back to a known good state. And so the key piece, and again, when I read one of these files from disk, even though I was careful to write it atomically, if there's any sort of parse error, I throw it away. I'm like, OK, now I'm going to create a brand new file. Yes, I might have lost some data, but I'm in a known good state, and I can still function. The funny thing about sending these things into the field is if something goes wrong, there's no ops team. Like, it's in West Virginia, and there's some merchant who doesn't give a crap about why it's not working. All they know is they now have a brick. So it's absolutely critical that it always come up, and that we always be able to, no matter what data we've lost, always be able to get it into a state where we can get it connected to the network so that we can remotely fix it for them. So the answer is, I said I didn't know the answer. I think I made it up. focus on the bring up, get that right, worry less about where you go down.
Okay, that sounds pretty similar to what we're doing, just didn't know if you had any other advice. Thanks.
Nope, no magic.
So we have time for one more question.
Somebody stand up.
Josh, I'm curious on your ARM device, any sort of hardware interaction, have you done any of that with Go, or is it all through kernel modules?
All through kernel modules, C shims, et cetera. We did a little bit in the early days, and we learned very quickly it's really, really worth it to have a small, preferably obviously correct, easy to reason about C program, and let Go handle all the tricky stuff. That was a quick one. Do we have one more? There was somebody up front here.
When you got started, how terrifying was it to start writing Go in this tiny amount of memory, and how did you reason your way through those fears?
Yeah, so there's a just so story about how it worked, and then there's the actual story. So the just so story is, we took a look at the options. There's C, there's Go, there's some of the scripting languages, and we weighed the trade-offs, and we said, okay, let's try Go. The actual story of how it works was my friend said, hey, I want you to come help with Beacon. I said, I'll do it if I can write it in Go. He said, okay. And in practice, that's how the world works. And there was a scary moment very early on in which we did our first cross-compile. We first SCP'd it over to the real hardware, and there was a SIGIL immediately. And I went and filed a bug, and within like 3 hours, Minix had diagnosed the problem and said we didn't have thumb on, and here's a fix. And I could go back 3 hours later and say, okay, now it works. And everyone was totally sold on Go at that point. And among all the decisions we've made in the course of this product, from hardware to the architecture, et cetera, basically, I think it's almost safe to say the only decision that no one has second-guessed is writing this bit in Go. I think that's a wrap. Thanks.